This is Module A1 Objective 5, and in this objective students are to identify the components of an enzymatic reaction and be able to classify reaction types. When we consider chemical reactions, we talk in terms of reactants and products. Reactants are the materials going into the reaction, and the example here we have propane plus oxygen gas. And the products are the materials that come out of the reaction. If you take propane and oxygen, you react those molecules, you end up with carbon dioxide, water, and in the case of this reaction you get a tremendous amount of heat and light. The reason we discuss reactions is because the body is constantly undergoing reactions. We refer to all the reactions taking place in the body as metabolism. So the definition for metabolism is simply all the reactions that are occurring within the body. And we can divide metabolic reactions into two main groups. We have anabolism. Anabolism or anabolic reactions involve the synthesis of molecules. You're physically building molecules up. If you think anabolic steroids used to pump up a bodybuilder, they're building muscle mass. This is where that term derives. So anabolic reaction or anabolism is the synthesis, while catabolism is the breakdown. Catabolic reactions break down molecules. And again, if you associate catabolism with catastrophe, hopefully that would help remind you that catabolism is the breakdown. There are several different types of reactions based on the reaction mechanism. And decomposition reactions, to decompose, to break apart, chemical bonds are broken. An example of a decomposition reaction is here, where you have AB, and these are just letters to represent molecules, and if that is then broken down into A plus B, this is a decomposition reaction. One example of a decomposition reaction is a hydrolysis reaction. Hydro refers to water, lysis refers to the breakdown, and if we were to look at a hydrolysis reaction, we have ABCDE plus water is going to yield ABC, and there's part of the water molecule plus the other part of the molecule linked to DE. This is a type of hydrolysis reaction. We've literally taken water and broken it down. Synthesis reactions refer to the formation of chemical bonds, and it's kind of the reverse of decomposition. In a synthesis reaction, A plus B is going to yield AB. So we've actually formed a covalent bond between A and B. Dehydration synthesis reaction or condensation is an example of a synthesis. Here we take ABC covalently bonded to hydrogen plus OH bonded covalently to DE gives you ABCDE plus water. You've literally taken the H from this molecule and the OH from this molecule, and you synthesized water. An exchange reaction involves decomposition followed by synthesis. So if we take AB plus CD, the first thing that would have to occur is a decomposition. You have to break the bonds between these molecules, and then you're going to basically exchange. A is going to bond to D, and B will bond to C, and that's the product here. So the reactants are AB plus CD, and the products are AD plus CB, the exchange reaction. Lastly, let's discuss reversible reactions, and these are reactions that occur simultaneously in both directions. Here we have AB, and we have a different type of notation. We have a double-ended arrow that is going to refer to the reversible reaction. And AB is going to reversibly end with the products A plus B. And this reversibility refers to the ability of this reaction to go forwards and backwards, and it will continuously do so. If we were to break that down, basically we have AB going to A plus B, and in the reverse reaction we have A plus B going to AB. So we actually have a decomposition reaction as well as a synthesis reaction, but it's reversible and it's occurring at the same time. In fact, when molecules undergo reversible reaction, they tend to reach an equilibrium. To remind you, an equilibrium, a balance, and at equilibrium the amounts of the chemicals do not change. You're still going to have the same relative amount of product as you would reactants, but the reactions are going to continuously occur. Once these reactions reach equilibrium, it's the balancing of that system opposes the reaction rates, and we'll look at this in a little more detail later on. Let me just think of a really good example of a reversible type reaction. HCl, which is hydrochloric acid, if placed within water, it's going to break down into these ions. And let's quickly classify these ions. What type of ion is this? Is it a cation or an anion? Well, hopefully you see the positive charge on this hydrogen ion, and you would classify it as a cat ion. And here we have the chloride anion. In terms of the reversible reaction, what is also taking place is the hydrogen ion plus the chloride ion is going to reversibly form HCl. In fact, if you take HCl and you place it in water, for instance, you're going to have reactions occurring in both directions until an equilibrium is reached. And then once that equilibrium is reached, reactions are still going to flow in both directions, but the relative quantities of products and reactants are going to remain about the same. The way that you do change the equilibrium is to add. If I were to add more hydrochloric acid to this situation, you're going to see a shift in equilibrium rates. But otherwise, this system will remain relatively stable. In terms of reaction types, often enzymes are required and to help get the reaction started. And in order to discuss enzymes, we have to define the activation energy. This is the amount of energy that is required to get the reaction started. It's often seen in a graph form, and if we were to follow this graph, at 1 here we have our reactants, and what we see is a very large hill. This is the amount of energy that is required to get the reaction to go, and this is our activation energy. Let's use an example that we've already seen. If we take propane, okay, and we were to add oxygen to it, what would happen? Hopefully most of you would realize that really nothing would happen. The activation energy for this reaction is very steep. You need something to increase the energy within this reaction in order to make it go. Does anybody know what what the energy input for propane and oxygen would be? Well, the energy input would be a spark, okay, a flame. We've all gone out and tried to use or watched someone use a propane barbecue. And basically you have propane mixed with oxygen, but before you can actually get the reaction to go, you have to add the spark. You have to take a spark and initiate this reaction. And that's the energy that is required to get it to go. That is the activation energy. Once we add a spark, our end products are the CO2 and the water and the tremendous amount of heat and light that is the byproduct. Enzymes serve or work as catalysts. And enzymes and catalysts, they tend to lower that activation energy. And this makes reactions occur very quickly without a lot of input. And there's lots of different enzymes in the body. They're usually proteins, and enzymes by nature are never destroyed. You never destroy an enzyme and need to rebuild enzymes. They're constantly being used and then reused over and over again. So activation energy.